taking you down to earth after this nice video. Let's see if this one's to go. Wow. I have to go down to go forward. Okay, so I'm representing I have two hats. One is the Norwegian Sequencing Center, which is a production facility or national Norwegian core facility for next generation sequencing, where we have FacBio, Illumina, HiSeq, and MiSeq. And the other hat is more a not that big but not that small either research group from the Center for Ecological and Evolutionary Synthesis, where the entire center is more than 100 people, but there's about, I have a mailing list with 33 members doing HPC, high performance computing and next gen sequencing data. I think 20 to 25 are doing it on a regular basis. And I'm basically taking that group's perspective in my talk. I'm not talking about the sequencing center, I'm talking about the people that receive the data from the sequencing center for their own research projects. So what do we do with this data? We have some big projects on assembling genomes. We have done the Atlantic Cod a couple of years ago. We're redoing it right now. We're working on bacterial genomes and metagenomes. This is the memory-intensive parts, for example, of the computing. We're also doing comparative genomics. We have both projects where we take entire genomes and make very well-established references of them and compare them. But our project is just doing a little bit of sequencing of many genomes to do gene mining. We have a SNP finding. We just started a big project doing resequencing of 1,000 Atlantic cod and 1,000 Atlantic salmon. And then we have all kinds of other. It's really a diverse array. So it's not. Our group doesn't have the possibility to make 5 standardized pipelines and that will cover everything. Everybody's doing their own little project, finding out their own little ways of doing stuff, which is one of the complications of our group. And this meeting actually is inspiring me to think about maybe we should do something about that. But basically all of us are doing bioinformatics. And it's also important to stress that we don't have any software engineers, we don't have any people with, very few people with a formal training in software engineering or bioinformatics or computing. So most of us are wet lab scientists by training that went into bioinformatics as soon as their disks got flooded with next-gen sequencing data, like me. So there's we have seen many of them already, different solutions to getting your infrastructure up. You could buy it yourself, reserve a room, put your servers in there, hire a sysadmin to manage everything, or teach yourself how to do that. You could have a university where you're lucky enough to have a very good high-performance computing cluster, preferably the number 100 in the world or something. Or you could use cloud solutions, either commercial ones or maybe your university has a cloud solution. University of Oslo doesn't want us to use non-University of Oslo cloud solutions for our data because they say we have our own solution, so cloud's out. We have decided to a mix on between self-owned and using the computer cluster of the university. We have both use for the computer cluster, where we have to apply for resources, and we have bought some of our own servers, basically saying with that purchase that we don't think the computer cluster is serving us enough, both in capacity and nodes. But we don't use those servers in our own offices. We place them in the same rooms. It's like the Finnish presenter had a very nice co-hosted or co-localized. And they trying to get rid of it, and we're still allowed to do it, so it's fine. So our servers that we buy are in the same location as the servers that the University of Oslo has bought. And this is the overview of what we're about to install. We have something smaller right now, which is going to go out, and I think they're unwrapping the boxes today and plugging the machines in. We bought with funds from 3 different sources, 3 high memory nodes and 16 grid nodes, so like 512 threads or cores in total if you want. And this again also reflects as we mentioned before, the wide array of types of compute infrastructure you need. For assemblies, we will need this 1.5 terabyte RAM nodes. But then there's the SNP genotyping, which you can spread easily on many, many nodes. And we have nothing in between, which sometimes is a bit of a drawback. We could maybe take one of those 1.5 terabytes and make 3 nodes of half a terabyte, which would be very nice for some applications. But the overhead for the HPC people to serve all our nodes is also quite big. So I'd rather have fewer nodes than many more nodes. Then we have an allocation on the supercomputer ABO, which in total consists of something like 10,000 cores or something. 8 of them are high memory, up to 1 terabyte of RAM, and there's something like 10,000 cores in the grid nodes. And we have applied for an allocation This is a national application that we can submit twice a year. We applied for several periods at the same time, and we got allocated 1.3 million CPU hours for every 6 months. And I'll come back to that. This is far from enough. Disk space, there's option to rent project space, which we now just recently increased to 60 terabyte, and I'll come back to the growth of that, because it's just, I think we're looking at a non-sustainable growth as one of my big challenges. We also have allocated on the national Norwegian storage facility some 50 terabytes disks and tape, and they're just starting with a national Norwegian archive for long-term research data, and I think we're going to put some data on there. We've got POIs and people can download it, and that's going to be it. Probably taking some of the load off. Now, in the disk space, of course, if you buy a server, you can put a rack next to it, which is what we do. So this is free disk. We buy it once and attach it to the server. It's quite fast, but it's only seen by the server. And we have disk that this is the 60 terabyte that we rent. And there's a backup to it, but it's much slower. It's more for non too frequent access data. And it's seen by the server, but also by the nodes in the cluster. And then you have kind of a scratch pace, which is more expensive, which is no backup. Actually, that should be a minus. It's very fast and can be seen by the cluster, and I think we're going to hook it up to the server as well. And the Norster is free, at least for now. The system is set up that the Norwegian government pays for that storage. There's no backup, unfortunately. The previous Norster had it, but currently there's no backup. So the basement of the building where all these things are standing is flooded. I think the data's gone. Not entirely sure, but connection is not directly, so we have to rsync data back and forth. They're working on mounting these disks on the cluster, and so they're not seen by any of our nodes. So basically, it's putting your data away for long-term storage. And the challenge is for both me as a researcher and for our group of freshly educated bioinformaticians to where to store what. How to prevent people from starting their process on the storage 60 terabyte, where read and write is slow. Also, it's giving a problem for the backup if many files are being written to at midnight. So a policy for data storage is something we're working on. And even though we write it all down on our wiki, people don't read it. We have the module system for software, which is really, really nice. It's a system where you can adjust your environment based on the program you need, and actually allows you to go back in time to old versions, so you can pick the version you want. This is fantastic for replicating old results, redoing something that your reviewers asked you to do on a previous version of a program. This is, by the way, the FOSSA 4 assembly program, Nuber. So basically, take module load Nuber, which would always take the last version, or you can specifically load one version from previous. And then we have a wiki, which I'll put the URL on back later, which is trying to collect all the how-tos and the procedures and the manual how to use this system. The workload manager is Slurm. I have for a long time complained about it because lots and lots of applications that we need use SGE, but Slurm is getting much more love these days. Lex, I think, is using it. So I'm getting more happy with it. I'm actually going to probably on 2 of the high memory nodes install Slurm for local use, that we are the only ones that can access to or submit jobs to those nodes. While for the grid nodes, the system is that if the nodes are idle, then anybody else can submit jobs, but those should be jobs that then are quickly taken off where we need the nodes. And for the high memory nodes, we have a mailing list system. It's really primitive, but it works. Basically say, I'm going to use this node for 2-3 days. And people should, of course, always do top when they SSH into the node. They usually work close fine. Hardly ever jobs stopping up because people are over accessing the node. This is kind of a history. So when we started to do the Atlantic code genome, we found out that the cluster, the high throughput sequencing or high throughput performance cluster from the university was not enough for our needs. So we bought 2 nodes, which are fairly small, 128 gigs and 24 CPUs. For the redoing of the code genome and for the increase in the project, we went to 0.5 terabyte nodes, 64 CPUs in 2011, and those nodes are now taken off and replaced by these ones. So it's increasing in the needs, and of course the price drives this possibility. In terms of the storage, and this is what I mentioned before, we started with 6.5 terabytes in 29, and we're now at 60, and I don't know where it's going to end. So I want a discussion with our group, can we try to reduce the amount of data we store on this area and spread it over more areas, particularly the ones that are free. disk is either new and empty or full, as a colleague of mine said, and this is true. These 20 terabytes are probably going to be filled up by summer. And everything stops up and people start complaining and I'm on holiday and I'm trying to fix it, so yeah. This is what we actually been allocated on the cluster, but we can apply for an increase in the amount of hours, and I think we're one of the few groups that always make their quota and ask for more. Some groups don't make their quota and quickly start doing all the calculations at the end of the period to prevent them from going down the next period. We have to ask more, and on average something like 2 million CPU hours per half year. This is going to be helped by our new grid nodes, we didn't have it before. So many of these 2 million are going to be over to our grid node, so we're going to reduce the pressure on the cluster. So why did we choose this solution? Well, sysadmin is always an issue when you have large computing clusters, and this is not me. I don't have to think about that. I don't have to think about power. I don't think about electricity or warming or cooling whatever city you want to cool. I don't have to think about cables or nodes breaking down and having to call service. So it's fantastic that I can port that over. I pay a fixed price, I pay probably something a bit more than if I would buy it in the shop, but it gives me this freedom to just don't think about it. There are very competent people in the HPC group that do all that. And the software, of course, you have maybe seen this graph. This is a graph of dependencies of programs, and they can actually be bigger. This is not the biggest I've seen. Not my problem. Of course, it's a problem if the IT people can't install it, but if they can install it, I will, of course, never be able to do it myself. So they're very good and specialized in getting all these packages to run and talk to each other and work with each other. And since they're a larger group than we can ever afford, they have specialties among them. So they can actually pinpoint somebody that will be able to fix this problem. The disadvantage, of course, that we have to ask them to do something for us, which means that we're going to go into their queue and may have to wait, especially if it's low priority or difficult. You have to make sure, if we want a certain software package installed for the entire cluster, it has to be something that more people use. So Noobler was easy because many people used it, but we also have the possibility to make local modules. And sometimes installing these things are then running into dependency hell, and they can help us, but it's a low priority for them. If the cluster goes down for maintenance or a big problem, then our system goes down as well. And this has happened, of course, if the cluster upgrades and our nodes are unavailable. So this is one of the drawbacks. We have less control. We don't control entirely what's going on there. Which file system they use, how they set it up, etc., etc. Of course, it means that we don't have to think about it either. We don't have to make a policy. We can, of course, ping them and try to influence the policy, but we don't control everything. And of course, I'm in the middle. I have to talk to both the users of the system and the people that set up the system. I'm kind of a man in the middle, and I get attacked once in a while. So this is still overhead for me. I'm trying to reduce that by making this wiki, which nobody reads, and sending links in the email, and trying to get people to update the wiki if it's not complete, etc., etc. But still, it takes some of my time. So I'm kind of a super sysadmin or whatever you want to call it. Now I'm gonna, and also, this is of course, if you have kitchens in your labs or in your groups, and the dishes are on the counter and not on the machine, this is the same thing. People don't clean up after themselves, forget to inform others what they do, waste disk space, etc., etc. Don't respond to emails. This is common. It doesn't matter if you have it in-house or if you use the computer cluster. I have a bit of a site. I'm trying this deliberately a little bit. This is a website I found from a workshop that I couldn't go to, which was in July last year, a reproducibility workshop at the Extreme Computing, I forgot the abbreviation. I'm going to quote from their final report, which says, organizational stakeholders, especially supercomputer centers, are in a unique position to promote, enable, and support reproducible research. And reproducible research, or replicatability, is one of my pet peeves. So I'm really working a lot with that, thinking a lot about it, so I implement it myself. And I talked already to the HPC cluster people, and they are aware of this, and I think we could do a lot. But of course, also in our group, we could think about it, and me as being the beneficial dictator for life, if you want, I'm trying to do something about it. And like I said, most of us are self-taught by inclination. We don't have this formal computer science education where I assume that the best practices for reproducible science are taught. So we have to after-educate, post-educate people. Create awareness is one thing. I'm trying to give presentations about it, trying to talk to people, I try to influence people, lead by example. And show what kind of good workmanship you can actually do. And I'll give you a few examples of what I mean with that. This is a good source for people. If you ever want to point out somebody to where to start, have them read this paper. And we'll also mention Software Carpentry, which is an organization that's exactly for the people that we are self-taught bioinformaticians, self-taught computer scientists in any field, how to teach them best practices. They organize 2-day workshops. We had one in Stockholm recently where I taught with a colleague. So I am an official software carpentry instructor, and we're trying to increase the amount of courses we can give, amount of workshops we can give at the University of Oslo and in other countries, to make people aware of and teach them how to do these best practices. The best practices we're talking about are, for example, automation of repetitive tasks. So that's why I'm really keen on the workshops tomorrow for workflows and on version control. And these two things are difficult. I mean, I can talk to people and say, it's important to use version control. And they go, yeah, sure. And I teach them how to do it. And that's the end of it, because it's a very big hurdle. And getting people that have done this, worked in this field for a couple of years to go over and use version control, in my experience, is very difficult. So the new approach we now have now is people coming in, the new PhDs, the new masters, will teach them or basically force them to do this from day one. We'll sit them down in front of a computer, use them, teach them Git and GitHub, and make them do that from day one. And we'll see how that works. Documentation, of course, very important. But also collaboration, collaborative code, pair programming, making your stuff available on GitHub so you can actually get further pull requests, people asking or suggesting changes to your code, making that code available with your papers. Don't be afraid to put preppy code out there, because it's you using it, so it should be good. Don't worry about that. Our researchers don't use Galaxy that much. University of Oslo just invested a lot of time and money in getting their own Galaxy instance hooked up to the cluster, so people can use both the allocations they have through Nutter and the login system from universities in Norway. But the take-up among the researchers is not that big, and I don't really know why. I'm not using Galaxy myself. I use it once in a while. I'm not very happy with it, but it should in principle be a solution for this kind of thing. So in conclusion, we have a mixed system where we go for, we're not completely satisfied with the cluster that the university has, and I think that should change. We should not have to invest money. In principle, the national Norwegian infrastructure should be good enough for us, but since it's not yet, we use precious research money to add some more. But I think it was very smart, even though it was at the time not a clear thought, clear conscious decision. I'm very happy with the decision. I would make it again, to place that infrastructure in the same rooms as the others. It's interesting that the Finnish people want to get rid of it. Maybe the University of Oslo at some point also wants to get rid of it, which would be fine by me as long as the cluster gets better. And it has its drawbacks and its advantages, but in general it works. It saves a lot of investment from us and a lot of time to train somebody internally to do this, etc., etc. I need to thank a few people, the Section IT-forskning, which is the people that actually run this. I'm extremely grateful for them. They're excellent, although they sometimes have a long queue. The Forskningsrådet, which is the Norwegian Research Council, which has partly paid for the infrastructure we use. The Center for Ecological and Evolutionary Synthesis, which is another donor. And the faculty, which also helped out with this infrastructure. And this is again our key. Thank you for your attention.
Thank you, Lex. We have time for one